Okay, now part 4, lecture 4a. What is a tensor? Okay, last video we talked about covectors, you see, vectors, and then this comes from the definition what is a tensor. Okay, let's split 1 and 2. Where is 2 here? Okay, 1 and 2. Let's talk about the definition of vector space capital V. A vector space over a field like real numbers or complex number is a set of elements called vectors, equipped with two operations. Vector addition, for instance, u plus v. U and v is an element of the space here, v. Okay? Vector addition, u plus v, and scalar multiplication. Lambda is a scalar. Okay, let's write here. Lambda is a scalar. Okay? And u is a vector, is an element of this space. This set, you see here, satisfies distributivity, in this case, associativity, distributivity, in existence of a zero vector. Okay? That's what you learned in linear algebra. Now, the new for you, for undergraduate students mainly, is a dual space V star. The dual space V star, attentional of V, you see, V star is related to the vector space here, okay? It's a set of linear maps, okay, from V to the field, usually R or complex numbers, real numbers or complex numbers. Okay, V star is defined as phi is a function, okay? That's V, okay? That maps on the linear map, in this case, linear number, okay? Real number, real number. Elements of V star are called covectors or dual vectors. Okay, that's important for you that in next videos you'll be using this terminology, okay? Now, in other words, V star is the set of all linear maps that take from this vector space and return a real number, or a number from the underlying field, like the real number or the complex number. In other words, elements of V star are functions that eat vectors and split out scalar in a linear way. You're going to give an example here for you to understand clearly what is this. These functions are called covector or dual vectors, okay? Or sometimes attentional is called one form. One form is related to the intrinsic geometry, okay, which doesn't have nothing to do with the extrinsic geometry. Yeah? This here can be applied to R3, as you see, and also to R4, okay, this intrinsic geometry. But I will emphasize extrinsic geometry only in 3 dimensions. There is no extrinsic geometry, for instance, in the Einstein field, okay, and the theory of relativity. There is no attentional, no extrinsic geometry, okay? Now, next, lecture 4b, you see, this is lecture 4a. I'll give example to make clear, okay, what I'm doing here, okay?